Hello friends, you are watching my channel e-learning, and today I'm going to teach you how to design a patch antenna in HFSS. So this is a series of antenna design lectures. There will be series. I will be designing different types of antennas that will include patch antennas, monopole antenna, dipole antenna. Then we will move toward the variable antennas, and then we will see how can we characterize the variable antennas. We will deform a structure, we will bend it, we will keep on the human body. Also we will see the SAR value for the variable antennas. Then we will move toward the MIMO antennas. Also we will give some touch towards the implantable antennas. So today I'm going to teach you how to design a simple antenna. Keep in mind that I always used variable to design patch antenna. Today I will design a simple patch antenna, and I will show you why it is necessary to design an antenna using variables. Because normally the antenna designers, they use numerical values, but when you try to optimize the antenna, then it becomes very difficult to optimize antenna, because you have to do a lot of changes if you make any single change in any parameter. So today I'm going to design simple patch antenna at 2.4 gigahertz, and I will design it using variables, and also I will design it using simple numerical values, and I will show you how and why it is important to use the variables. So let's start. So in designing antenna, first of all we have to make some changes to the modeler. So for me, I always prefer to go for the I will go to solution type first of all, and I will change this driven model to driven terminal. Okay, so the first thing you need to do, you need to go to the HFSS, then modeler, and then you have to change it to driven terminal. Okay, now you need to design a substrate. First of all, you will design a substrate. So for a substrate, you need to go to this box, draw box. I will just draw this box. Okay, now what I will do, first of all I will change its name to substrate. Okay, which material I'm gonna use? So for substrate I'm gonna use FR4 substrate, which is normally available. And now I will click here to change its dimensions. So I'm telling you that in the first design I will be using variable, and in the second design I will be using simple numerical values. So for the variables, suppose I'm considering that on x-axis the width of the end substrate is WSUB. Suppose I'm telling it's WSUB, and the length of the substrate is LSUB, and I'm starting it from 0 point. So what I will do, I want to keep this antenna symmetric around the y-axis and x-axis. So what I will do, I will start from half of the width and half of the length. Okay, then when I will move toward the x size, y size and z size, it will ask me about the values of WSUB, LSUB. So suppose I'm keeping both of them as 60 mm, and I'm also keeping this as 60 mm. Okay, and from x size I will keep it minus WSUB, and the y size I will keep it as minus LSUB. The z size, this is the shows thickness of the substrate, so I will keep it as HSUB, height of the substrate. So height of the substrate is 1.6 mm. Normally for FR4 substrate, the 1.6 mm thickness substrate is very commonly available in the commercial market, so we are using this one. Then we will here make it fit view, and we successfully designed our substrate. Now the second thing, we will go and design the ground. So for ground I have to come here, draw rectangle. I will simply draw rectangle, and first I will change its name to ground. Okay, then I will come here, and the ground will be equal to the length and width of the substrate, so I will be using WSUB by 2, LSUB divided by 2, and 0, because ground will be on the 0 plane. The X size will be minus WSUB, and it will be LSUB, sorry, minus LSUB. So this is our ground plane. Now you can see the bottom of the substrate is the ground plane. So we just draw a ground, but it is unassigned. It is nothing if you technically refer to it, so it means it is nothing now. So what we will do, we will assign, we will make it perfect E. We will come to assign boundaries, perfect E, and okay. So now this sheet is a copper, it will behave like a copper. Okay, so any metal we will be using in this design, we will assign it as perfect E, so it will work as a perfect copper, a perfect conductor. Okay, now what we will do, we will make a transmission line. From here we will make a transmission line, and then we will design the patch. Okay, so for transmission line, again I will take this rectangle, and I will simply draw it. First I will change the name, and I will make, okay, I will name it as transmission line. Okay, so transmission line. Now I will, okay, my transmission line will be here. It will start from here and will go on this way. So my x-axis is here and my y-axis is on this direction. So this is y-axis and this is x-axis. So from x-axis we will start it from WSUB divided by 2, because this whole thing is WSUB, but the first point, always we take first point from the 0, 0 and 0. So this is our reference point. So from reference point to here, the total distance is WSUB divided by 2, because the whole distance is WSUB. So this is WSUB. Now the second thing is how much will be its, what will be its position in the y-axis. So I will call it WS strip, or I will call it WTL, width of the transmission line divided by 2. So I'm starting it from here, okay, from the positive side of the y-axis, and it will be on top of the substrate. Now it will ask me the length of transmission line. So the length of transmission line, I already know that for FR4 substrate having thickness of 1.6 mm, its transmission line is 3 mm, so that it can transfer the maximum power to the patch. Later in my later videos I will tell you how you can calculate width of the transmission line. Okay, now what will be the length of the transmission line? So the length of the transmission line, I'm telling it will be LTL. length of the transmission line, and it will start from here and will go towards the negative axis. That's why I'm putting negative sign here. And suppose I'm telling it will be 10 mm. And what will be the size of Y? So Y will be actually the width of the transmission line, so it will be WTL. So this is my transmission line. Now I will assign it as perfect E. Okay, so this transmission line is now TL. Okay, so this TL is now copper. It will act as a perfect copper. Now I have to design a patch. For patch, again I will come here, select rectangle, and we draw it like here. First I will change the name patch. Okay, now okay, so as I told you that the first point, you have to take the first point from the zero center. Okay, so I will start it because I don't know what is this position now. So how I know this position? I know from here to here is WSUB, and from here to here is LTL. So my point will be WSUB minus LTL. That is the by 2, and y-axis will be width of the patch. So I'm calling it WP, width of the patch, divided by 2, and I'm designing this patch on top of the substrate. Okay, so my WP, I'm initially taking it 38 mm for because I'm designing antenna at 2.4 gigahertz, so I'm taking it as 38 mm. So my x-axis, this is my length of patch, and I will call it LP, and I'm putting the negative sign because it is moving towards the negative axis. I'm taking it as suppose 29.5 mm, and my Y size is minus WP. So this is my page, this is my this is my transmission line, this is my page, this is my dielectric, and below the dielectric there is ground plane. This page is now unassigned. I have to assign it as perfect E. So this is perfect E. Okay, now the next thing is to design a port, because we have to give signal from here. Okay, so we have to design a port here. So what I will do for a port, I will first make here, because now every rectangle we are drawing, it is in XY plane, but if we want to keep a port here, so it should be in Z axis, Z plane, and Y plane. It should be in YZ plane. So I will make it YZ plane, and from here I will draw one rectangle like this, and I will call it port. Okay, I know this position, this is WSUB, and I want W port as width of this port, W port 2, and I'm trying to start it from 0. So suppose my W port is 5 mm. Now the Y size will be minus W port, and the Z size will be HSUB. Where is port? Oh, Now you see the port is here. Here is the port. Now I will assign this port as lumped port. Okay, so I will go and I will go to assign excitation. I will go to lumped port. Now this is asking me reference for this. So our reference is ground. So I tick ground as reference. So you see this type of excitation is really, how to say, easy from the Dremel model or the other model. So that's why I'm using the terminal model. Okay, so everything is okay. Now what I can do now, I can unite this transmission line and patch. This is up to you. This is not necessary that you have to unite it. You can do it without uniting, but to look feasible to me, to look good to me, that's why I'm uniting it. So I will select one, then control, then select other, and then I will unite it from here. Now it seems one object. Okay, also you can change color of these substrate, ground and everything. Suppose I want to change color of this substrate is green. This is green. I want to change color of ground. Suppose this is the ground. Now you can see your ground is like this. Also for the patch you can change the color. Suppose same color here, you see. Okay, the next thing, you need to design a radiation box. Okay, keep in mind that always you have to design a radiation box which will be lambda by 4 away from edges of the antenna. So now the edges of the substrate, we will consider it as edges of the antenna. So you have to keep in mind that the radiation box should be lambda by 4 from the edges. Okay, so I will design one. Okay, first we need to change this to xy, and then I will go for a box, and I will tell this box as radiation box. Okay, and I will change its transparency to this thing, so that I can see inside the inside of this box. Now I will call it a box box by 2, box by 2, and box by 2. Okay, so if I calculate lambda for 2.4 gigahertz, it will be 125 mm. Okay, 125 mm. And if I calculate lambda by 4, so it will be 31.25. So I know my how to say, length and width of the substrate. My length and width of the substrates are WSUB and LSUB, both are 60 mm. So what I will do, I will do one thing. I will write it WSUB divided by 2 plus 31.25, so I will make it 35 mm. So what it will do, it will add 31.25 to each side, and this will come minus box by minus box and minus box. Sorry, I did one mistake here. Okay, from this is the box. Okay, I can do one thing. I can change this thing from here. The box size, I keep it as 60 plus 35, so it will be 95 mm. Or I can keep it as 110. Okay, now this is my radiation box, and inside the radiation box this is our antenna. From here I will make one change. Now if I select anything, it select the whole object, but now I want to change faces, so I will check select face, then I will select this all faces of the box using the control. Okay, I selected all sides. Now right click, assign boundary, and from here I will select radiation, and it will be as default. Now from here I can see the boundaries. This is my ground, this is my patch, and this is my radiation box. I can see that whether I assign the correct boundaries or not. Okay, now we have to do some we have to tell HFSS that okay, on which frequency we want to simulate this antenna, from which frequency to which frequency. So we can do this by coming to analyze portion, add solution setup, and as I told you, I'm designing this antenna for 2.4 gigahertz, so I put it 2.4. This is not necessary, I can put anything here, but I designed my box at 2.4 gigahertz, that's why I'm putting my solution frequency as 2.4 gigahertz. After this I will come here to setup, well, add frequency sweep. Frequency sweep I will make it fast. I don't want to save any fields for now. Okay, and I'm looking this antenna from 1 to 8 gigahertz with step size of 0.1 gigahertz. Okay, now if I analyze my antenna, so my design setting is okay, my 3D model is okay, my boundaries and excitations are okay, my mesh operation is okay, analysis setup is okay, optimetrics are okay, and radiation box is okay. So I can run this design now. So I'm running this design now. This is the analyze all button, so you have to press this thing. We have to wait for the setup to run, then we can see okay whether our antenna is okay or not, on which frequency it is working. Okay, so the setup is already run. Now I will come here to results, right click, and then terminal, solution data, rectangular plot. Okay, this is already by default S11 and the function is SDB, so I will new report. So you can see if I add a marker here, so my frequency is around 2.3 gigahertz. Okay, these are the further harmonics, but you can see the peaks are not below minus 10 dB, so these peaks will not work. Although we can make some changes to the antenna to remove these harmonics. Suppose if I told you I'm okay to design my antenna using variables. So What advantage these variables have? Suppose I want to change length of the transmission line, so this page will automatically adjust with this. Suppose my transmission line is now 10 and I want to make it 15. Okay, 15. So you can see my page is already adjusting with it, and I can analyze like this. Okay, and from here I can make it accumulate so that both design I can see together what was the previous results and what is the new result now. Okay, we have to wait for it. Okay, so this is the new results and these were the previous results. Okay, now let it be. We don't want to optimize this thing. You can do it by yourself to perfectly match it or what you want to do with it. But the second thing is we want to see the radiation pattern. So for the radiation pattern you need to come to the radiation. Okay, right click on it, insert far field, setup and infinite sphere. In this you will, the start will from 0 to 360 and 10. Also you need to make this as 360 and 10. Okay, now you didn't save any frequency, but we want the radiation pattern at 2.4 gigahertz. What we will do, we will come here, we will right click, add frequency sweep, and from here we will make it discrete, and from here we will make it single point, and we will make it 2.3 gigahertz. I will check this thing. Okay, now I will click on it, right click and analyze. Now I'm only analyzing sweep 1, 2.4 gigahertz. So I will again come to results, right click, far field setup. Okay, suppose I'm looking to see I'm going to see the radiation pattern. So from here I will go to sweep 1, because at sweep 1 I stored 2.3 gigahertz frequency. From here I will select gain, this will be total gain, this will be dB. From families I have to, okay, I'm looking at I change the parameter LTL from 10 to 15. Then they are asking me whether you are looking at LTL 15. So I'm saying yes, I'm looking at LTL 15. But this option normally doesn't come like this doesn't come normally. Okay, from pi I will check at 0 and I'll make it like this. So this is my radiation pattern at pi 0 plane. What about pi 90? I will make it 90 and I will keep it at trace. So I got two radiation pattern. This one is for pi 90 and this one is for pi 0. Also I can see 3D polar plot from here. I will select far fields, I will select 3D polar plot, I will select sweep 1, I will select gain, I will select dB. Okay, I will go new report. So this is my 3D polar plot, and from here you can see that the maximum gain is 3.6 dB. Okay, so this is the gain. Also you can check the current distribution on the page. So we'll do one thing, I will remove visibility of the radiation box. I will select patch, right click, plot fields. This is the E field, suppose magnitude of E or surface current. Okay, and I will come here, make it sweep 1 and we'll do it, done. So now I can change the scale from here. Okay, if I make it 5, you see. So I can also animate this thing. We'll right click on it from here and I will animate. You see, with this thing how your fields are varying with different phase. Okay, so this is I designed this antenna using variable. In my next video I will be designing the same antenna using constants, directly numerical values, and then I will show you that okay, why variables have advantages over fixed values. Thank you.